Hey, John Gilroy here. We see malicious actors are taking data that's encrypted today. Let's look at a new concept called harvest now, decrypt later. Hit the music, Manny. Welcome to the Federal Tech Podcast, the podcast that connects you to federal technology leaders. In the virtual studio today is Eric Hay, Director of Field Engineering at Quantum Xchange. That's XCHANGE. Eric, encrypt now, decrypt later. Why worry about all this stuff?
Yeah, I think that's a good question, John. Thanks for having me on the podcast. I think the challenge is that if you have data that you care about the privacy of today, and in some cases the integrity of, then you should be thinking about this particular challenge, because I can copy data on the internet today. That's why we encrypt it, because you can't keep people from seeing the packets, so people can copy it. But I could copy it today and store it somewhere. And then the quantum threat is when I get a quantum computer, I can use an algorithm called Shor's algorithm, and I can decrypt that data. So now I can see what you sent. So imagine all your secrets, all your bank account information, all your PII, your state secrets, your design plans for the next gen stealth fighter. Imagine all that is transmitted over networks as people are working on these projects and conducting business. And now in the very near future, somebody comes back and says, oh, I copied all that data that I was interested in, and now I can see what it is. That would be a bad thing. I think we can all agree. You know, we value our privacy, and some data needs to be more private than others. But yeah, that's really the threat.
Yeah. I'm a very sophisticated intellectual, and what I did to do show prep, I went to Google Trends, and you could do this if you're listening, and I typed in post-quantum cryptography. And, you know, it went back 14 years or something, and it was pretty flat, you know. And all of a sudden, now we have a hockey stick here. So I don't know, if Eric, if you're betting on the right horse here, but there seems to be a lot of general interest in the United States government, outside the United States government, corporations, for understanding this whole concept of quantum cryptography. I thought we'd bring in and talk to you here. It's not something brand new. We see peaks here in interest, but the government's working with several standards for this, aren't they?
Yeah, that's right. And actually, you know, a shout out, if you will, to NIST, because they've done an amazing job of herding a global community of cats, first of all, in getting people to review these algorithms and have a very open and fair assessment process, so that people could say, hey, we think this is flawed, or we think this isn't going to perform well, and have a lot of input. So it's not just the government mandating that we do something that they've approved behind, you know, closed doors. It actually is a very open process. And that's why the NIST reviewed and approved now algorithms, ML-CHEM 1024 is one of them, are now recognized around the world as ones that probably should be used. And that's not true everywhere, as you can imagine, but certainly true amongst most Western countries and obviously U.S. allies.
I think there's another one, OMB, was it M2302? Is that the one you referenced? But so that they're working at it from several different levels, aren't they?
Yeah, because you have to do two things. One, you have to approve a standard, right? You have to validate that something is safe and secure, and that's what NIST job is. And then you need somebody from a policy perspective to say, hey, we need to start using this in the government. And just as an example, this has happened before. So way back in the day, we created the advanced encryption standard known as AES, and the government said, hey, if we're encrypting data, especially data in transit, we need to use this new standard that NIST has approved. And so they basically made it mandatory. And that's where we came out with like FIPS 140. That became a government standard. And then once it became a government standard in the US, it becomes a government standard, and then it sort of filters down to private industry, right? So like banks will have to use it, in part because they're worried about litigation, right? If it's the minimum standard for the government and you don't use it to protect your customers' data, you might get sued. Right? That's the way it works in the US. In Europe, it works a little differently. In Europe, they actually mandate that a type of data must be protected using a certain method, maybe a certain algorithm, no matter who you are. So that's government and private industry. And so they don't, that's kind of an interesting way to do it. I'm not sure that's possible in the US, but certainly different ways to approach it. And everybody is moving towards post-quantum cryptography because of this threat, right? Harvest now, decrypt later. And then the other thing is, what happens, John, when we wake up one day and it's Q day? It's like, we knew Y2K was January 1st, 2000. Yeah, we knew that day. Yeah. So I did a lot of Y2K remediations. People said, hey, it wasn't really that big a deal. And I said, there was a literally army of thousands of people, tens of thousands of people that worked, and just in the US, that worked to mitigate all these things. And we would have had servers go down, disk arrays were all needed to be updated. And there was a lot of work that happened behind the scenes. So that, yeah, it wasn't a big deal. It wasn't a big deal because it wouldn't have been impactful if we'd done nothing. Stuff would have broken. But we did a lot of work. We need to do that same work now so that when we wake up on Q day, we don't say, oh, all my data's been compromised. That would be a bad thing, I think.
On December 30th, 1999, I went on national television, NBC, and they asked me to predict what was going to happen. And then they had me on call on New Year's Eve if I had to come in. Well, I made the right prediction. I said, go to sleep. Don't worry about it. You mentioned Europe earlier. Let's go back to Europe. There's a part of northern Spain where they have this long walk to some place called Santiago. It's called the Camino del Norte. And so Camino, I think in Spanish, it's like a journey, a way. And when I take and apply this maybe to the federal government, if you look at 135 agencies, there's different journeys that people have towards post-quantum. So from your view, what kind of a camino, what kind of a way are these agencies? Are they just starting? Are they intermediate? Are they adapting these standards? Or are they just too scared?
No, so they are. And again, NIST, part of what NIST does is create standards and then also procedures or guidelines that organizations, government organizations, should use to implement certain things. And so they have a workflow or work streams created to help organizations, help government agencies basically migrate to post-quantum cryptography. And there's really sort of 5 things you have to do. The first is you have to figure out where your encryption is, right? I can't fix it if I don't know where it is. That's a hard problem, by the way. The second thing is you have to figure out which ones to do first, because you can't do them all at once. Encryption is everywhere. It's in your badge readers, those devices you check into the building with. It's in the badge reader, it's in your network devices, it's in your phones, it's in your laptops and applications, the postage stamp machine, it's everywhere. So you have to figure out where it is, what stuff you want to do first. Then you have to deploy it, right? Then you have to monitor, make sure it's running right. And then you have to manage it. And you're going to continue to do that until you complete. So this is a sort of continuous lifecycle management. So they've really done a good job of that. And a lot of organizations are still in the discovery phase. Like, where is my encryption? Now, at Quantum Xchange, we think there are things you can do today to move to the deploy phase. We are working with government agencies that are trying to do that, and we can talk about that in a little bit. But basically, there's some things you have to do. It's not a snap-in algorithm replacement. And I think that's kind of maybe if there's a misunderstanding out there in the market, is that we are not going to be able to take RSA, which is what we use today for a lot, or ECC, which is elliptic curve cryptography. We're not going to just take these algorithms and take them out and put a new one in. It's not that simple anymore, right? Because these are new ways of computing secrets, and they require more horsepower. So some devices may not be able to do that. They require bigger sets of data. And why that's important is if I'm running like RSA on my network and I try to put in the new CHEM, which is the NIST replacement for the RSA key exchange, right? The problem is the data that it needs to exchange with CHEM is much bigger than with RSA. And so why is that a problem? Well, the problem is we've built a legacy infrastructure with legacy protocols like TLS, right, which is what we use for HTTPS traffic. We have network infrastructure that is based on basically a frame size, basically the size of a packet of data. Think of like an envelope. The envelope is only a certain size. If we try to put the new keys in for these new algorithms, they don't fit. So now you got to break it across 2 envelopes. Well, that's a problem, because what if the envelopes get there in the wrong order, right? These TLS protocols weren't made to handle that. It assumed there was 1 envelope for the key, and now we're going to have to break it into 2. And the next set of algorithms, you might need 3 or 4 envelopes, and the ones after that, you might need 10 or 20, right? So this is becoming a big problem. It's not as easy as just dropping it in. And I've been to forums where they say, oh, we have new certificates that use these post-quantum algorithms. And I said, well, that's not going to work. Like, it might work for certain very edge cases, but for 90% of the stuff out there, it's going to be a problem. So these are all challenges that we kind of have to deal with when we talk about this, right? And the one thing is, it's not a snap-in replacement. I'd say the other thing that people may not understand is that, we've been really lucky, John, that we've had Moore's Law. You're familiar with Moore's Law, that, compute power is going to double every 18 months to 2 years, right? And so when you're looking at cryptography, there's always this sort of cat and mouse game, right? When is this going to break? When do I need to make longer keys? Usually when computing gets faster, you just make your encryption keys longer and then you buy yourself some time. We've been able to predict that pretty easily. Well, we call quantum and AI, because remember, we're in a new era of computing. I call those the toddlers of next gen computing. They're not fully formed yet. They're just hitting the playground. We kind of know what they can do, but as they mature, stuff is going to break. And if you think about how we've, compute power has increased over time, it's kind of like going from a 2-cylinder engine to a 4-cylinder engine to an 8-cylinder engine, right? We have faster CPUs that can do more things. And so you could drive, if that's in your car, you could drive from New York to, Boston in, a certain amount of time, and you're cutting that in half. And so we're going faster and faster. Quantum is not that. It is not, and AI even is not that. We created a rocket engine, and we're not going from New York to Boston. We're going up in another dimension. This is going to happen so fast and at speeds we've never understood before and be so disruptive that we have to understand that Moore's law, which allowed us to say we knew when RSA 512, 768 would likely to be broken. We knew we had to move to, RSA 2048. The government knew, NIST gave good guidelines. This was great for us. Those days are over. We don't know the pace of change. We just know it's going to increase. And so what's the impact of that? Well, the impact is that we should assume that if you deployed a post-quantum algorithm today, we might wake up one day and find that A, it's been broken, or B, at a minimum, we have to lengthen the keys, right? Which now I need bigger envelopes, right? So those are non-trivial problems. And I think when you talk to, organizations, they don't really have a grasp of that. They say, hey, we've had RSA since 1977, so that's almost 50 years. We're going to put the new one in. We're just going to swap it out, and we'll be good for 50 years, right? But the world's changing, John. So that's the challenge. I mean, I'm sure you're seeing that, right? Where people don't understand the impact of quantum and AI and what it's going to do. And this is a new world, and we better prepare for it.
I taking notes here, and I wrote down Back to the Future. Remember the one episode Back to the Future where they said roads? We don't need roads because they're beyond roads. So RSA is maybe the roads, and quantum is we don't need no roads.
Yeah. You put the banana peels in the Mr. Fusion and you take off. Exactly right. Yeah, and that's important because I think we're trying to gauge the future based on how we've experienced the past, right? That's kind of what you have, but you have to have a vision to look beyond that. And so we're really encouraging organizations and specifically federal agencies that we're working with to kind of look at this in a slightly different light, and maybe that will help them more properly prepare for what's coming.
Let's play with this word vision because, again, I'm so sophisticated. I went to Staples yesterday, bought a paper calendar for 2026, and it's kind of a backup calendar, put stuff on it. So let's say we give this calendar to old Eric here and say, okay, Eric, take a look at 2026. So what kind of practical tips would you give to CIOs or CISOs in the federal government for maybe building this roadmap or camino or way to post-quantum?
Yeah, so I would say that one thing you want to do whenever you plan a trip or a journey is you need to figure out where you're going, right? And then you want to figure out maybe the fastest way to get there. And what you want to do is you don't want to take too many, so let's say I'm traveling somewhere and I know that I can't drive there, so I have to take some combination of plane, bus, and train or something like that. You want to try to get the most amount of the travel done in the least amount of time, generally speaking, right? So what I would encourage people to do is start thinking about, instead of thinking about these new algorithms and how you're going to deploy them into every endpoint, because up until now, encryption has been very endpoint centric, meaning the application does it, the operating system on the workstation does it, the network device does it, and it does all of it. It generates the keys, it exchanges the keys with a peer, it operates and manages the key lifecycle, and it just repeats and does that, right? And I've said this many times, which is we've really been lucky that we've been able to do this for about 50 years and sort of set it and forget it, right? The problem is we're not going to be able to do that anymore. And so for an organization, we say, if you're thinking about this journey, what you want to think about is not that you're going to do every single application and every single endpoint and go through this NIST work stream right away, because you can't. What you want to think about is what are the things that you can control right now that give you the biggest return from a security perspective with the least amount of cost, effort, and disruption, right? And so what are those things? Well, there might be specific applications like cloud apps that you use that you could do. That's one. The other would be in your network infrastructure. If you're managing data transit from A to B, like headquarters to a branch office or to the cloud or to a data center, why instead of doing every application that's using that network transport, why wouldn't you first just do the wire? I can encrypt the wire between those two places, and then all the traffic in it is encrypted. So going back to the Camino, the road, the way, if I encrypt the path, the way, all the footsteps in that way are protected, right?
Yeah.
So that's a much better way of thinking about it. And you still have to do certain apps, and there's a lot of other things that have to happen on the endpoints, and we get that. But we think that there's a value in looking at it from a network-centric approach, because remember, the quantum threat is harvest now, decrypt later. That's today. Well, that's a network transport problem. If I fix the network transport layer, well, I've kind of solved that, right? Whether I can do the badge reader or not, if I protect its traffic, I've solved that issue. So that's a way to think about it. We think is really important for people to just kind of change the vision a little bit, change the perspective, right? Part of vision is perspective. So change your perspective a little bit and say, hey, if I can do the wire, I can make a lot of progress towards getting there. I still have a lot of work to do, but boy, for a pretty simple effort, I can lock down a lot of my infrastructure and get a lot done quickly.
When if you and I were at a coffee shop and we talk about AES, my little brain would focus in on the algorithm, and I'd go, oh, it's just like when you had to learn all that RSA stuff that years ago. You just focused on it because But really, it's back to it's not your father's Oldsmobile, it's not the road, because we got to worry about architecture, government, operations. I mean, okay, you got the algorithm down. So what? I mean, now you have to put it in perspective here, because there's so many hybrid architectures out there. We're not talking about only air gap systems. We're talking about systems that are everywhere. So this gets to be almost an architecture question in addition to the algorithm problem, doesn't it?
It is. And one of the things that if you think about, let's take a simple, Alice wants to communicate with Bob and they're currently using RSA to do that. If that is vulnerable to the quantum threat of harvest now, decrypt later, or on Q day, understand that on Q day, what it would mean is instead of harvest now, decrypt later, I can sit in the middle of any conversation that's encrypted. I can take in real time, break the encryption key, and then not just see the data. I could modify any data sent between Alice and Bob without being detected.
Yeah.
So when Q day gets here, as I say, very bad day if we haven't fixed that. The challenge we have is if we just simply replace the RSA algorithm with ML-CHEM, the new NIST algorithm, or any of the NIST algorithms.
I would do, yeah.
Yeah. Well, okay, that's great. Right. Well, so what have we done? Well, we're just hoping that ML-CHEM doesn't break because I have that same architecture, right? And so man in the middle, because the key is negotiated with the data, right? We've treated keys as data because that's how we've always done it, right? And so we treat them as data, and if we keep doing that, we're just hoping that the algorithm doesn't break. I always joke, I've said this a million times, and I'll say it again, that hope is the least effective yet most widely deployed cybersecurity strategy. I hope nobody finds out that password. I hope it doesn't break. I hope nobody figures out we deployed it improperly. I hope the algorithm doesn't break. So what we would say is that from a architecture perspective, the quantum threat is as much an architecture problem as a algorithm problem. The fact that Alice and Bob negotiate the key directly means that the man in the middle opportunity to get the key and the data together and go hack at them for however long it takes to break that and have everything I need still exists. So why don't we think about maybe doing some different things? So think about, how do you identify yourself to your bank when you go do a bank transaction? Well, you have your phone, you log in, but you might have to go and do like Google Authenticator, right? Or some other authenticator app that gives you a token that is delivered out of band from your network connection to your bank. And then you can validate. So you've got a third party that you trust. Well, that's just a service. And that could be a service that's completely run by the bank. So there's no external, they have their own authenticator, or it could be, some globally shared, Google, Microsoft Authenticator kind of app. Well, interesting. So what if we did that with encryption? What if we said when Alice and Bob want to talk, they don't negotiate a key directly over their data connection. What they do is they talk to a trusted third party or a trusted set of infrastructure in the enterprise and said, Alice says, hey, I need a 256-bit AES key and I need it to go to Bob. And now that key is delivered to Bob and delivered to Alice out of band. And now they use it to encrypt the data. And so if you do that, what have you done? Well, you broke man in the middle because the key isn't there anymore. In fact, the attacker can harvest that data all day and night, doesn't matter. The best they can ever do is guess the encryption key. and guessing. If you force the attacker just to guess randomly, that's as good a security as you can get. So that architecture is something that protects you if an algorithm is broken, right? Because the harvest now decrypt later only works if the key exchange is in that pipe. So that's sort of one way to think about it. Does that make sense to you?
Yeah. I'm sure listeners have big questions, and what I'm going to direct them to is your website. It's Quantum, QUANTUMXC.com, and get more information on that and learn, because this gets so complicated. I mean, just AES is a 3-hour interview about AES.
It is.
I mean, hold it. I mean, because we learned a lot so far, but wow, we're running out of time here, so I'm just going to toss this one question at you. Sure. When's Q-Day going to be? Put it in your. I'll put it in my paper calendar if you want. When's Q-Day going to be? Give me a name. Give me a date.
So dates in the calendar may be closer than they appear. I will use that mirror. So I think people had been recently talking about 10 years and then 5 years. If you talk to the people that build the quantum computers, these are the publicly traded companies that of the world that do it. They're saying 3 to 5 years now, and 3 years is really short. In Europe, there was a update. I was just on a call with our colleagues at NIST with some European partners, and they've pushed everything up. They want everything done. I think by 2029, they want migration to PQCs. I think that's what they're pushing for.
Yeah.
Boy, that's extremely aggressive. And it's done because they believe that we have underestimated the adversaries' abilities relative to quantum computers. Like, remember when DeepSeek came out and we realized that maybe the adversaries had been our competition, global competition, were farther ahead in AI than we had suspected? Well, they've been spending on quantum longer than they've been spending on AI. So we should expect that this stuff will start to break. And again, on Q-Day, it's going to be a bad day.
I think Americans are traditionally underestimate their opponents. It's what Americans do. Because big country, we got a lot of smart people, but I think this is something that is it's a different category completely. We can say all kinds of jokes about Back to the Future, but it's not the road anymore you're worrying about. You're going up, and it's a different perspective. And I think it's so difficult because you're trained to think about mathematics and algorithms and RSA and AES, and we all took those stupid tests, and it's just it's a whole different way to look at it. So maybe the next time around we'll do some projections at different agencies and say, here's the maturity level of one agency or another agency, and see how important this stuff is. It's a great topic, though, isn't it?
Well, keep your eyes peeled, because I'm sure there will be some announcements in early 2026 of agencies that have started to take some pretty significant steps here. So we're working with some of them, and there's other folks in the industry that are working with them. So we expect that the government's really taking a leadership position here, whether it's starting with NIST and now with the agencies that are sort of forward thinking and have particular types of data, long-term assets, data assets they want to protect. So they're moving pretty quickly, and I'm encouraged. So I'm encouraged by my government. I'm less encouraged. I'm less sanguine right now about private industry, but they'll catch up as soon as the government makes some announcements. I think then the private industry will jump in.
I love to end on optimism. Me too. I'm optimistic. You have been listening to the Federal Tech Podcast with John Gilroy. I'd like to thank my guest, Eric Hay, Director of Field Engineering at Quantum Xchange.
Thanks for having me on.